Welcome back to Efficient Algorithms, COMP526. In Unit 6, we'll do a brief excursion to error-correcting codes. This will be a much shorter unit than the compression unit, not because there's much less interesting things to say about error-correcting codes, but I think for an algorithms class, there is indeed more interesting algorithms in compression than on this topic, but maybe it's also my personal bias. I do want to show you a few nice little highlights of error-correcting codes, though. The outcomes are that you have some understanding of the context. You know what's possible there and the distinction between detecting errors and correcting them. You should understand the terminology of block codes. We'll come to that. And we'll have essentially one concrete set of codes, the Hamming codes, that we'll look at in detail. And then, again, finally, applying the knowledge is more important than knowing all the details alone. You should be able to judge when such a code is suitable to solve a problem that you're facing. Very short unit, as I said. I'll give a quick introduction, and then tomorrow we'll look at what's not possible and then what is possible. So I said there's some philosophical connection to the previous section. What it is about is we're somehow in both these units thinking about getting data from one point to another. And if you do that in a computer, you have to encode things in bits, and then you have to get those bits from A to B. Now, it's useful if you have few bits to get from A to B, because then communication is faster and so on. So compression is often used to reduce the amount of information you need to transmit. But then for the transmission itself, you often have noise in the communication channels that you're using. We're very used to this, so when I speak to you, there's acoustic noise from the room, hopefully in a good lecture theater, and with using the mic properly, not as much, but it's never zero. I might not pronounce things very clearly sometimes, or other people, maybe I'm doing this perfectly, but other people aren't, or whatever. Make your pick, but you can certainly imagine situations where that's a problem. And then, of course, there's more semantic things to it, too. That's what humans have clearly in their forms of communication as well. Now, we've also found ways to work around that. One option is if you can't understand what someone says, if the noise is too much compared to the signal, then you just ask them to speak up, or maybe repeat what they said, or speak more slowly, or various options like this. Often, we can still make out what someone said despite all the noise. And if you think about this a bit more abstractly, or a bit more from the higher level, how is it even possible that we don't get all the information from the other communication partner, from the sender, and we can still make out what they meant? Okay, some of that might be we just fabricate a meaning that they may never have intended, but that's not what I'm getting at here. What I mean is our language and the way we communicate has a lot of redundancy built in. There's a lot of things you can do to, for example, the spelling of English that doesn't affect how well you can read it. Now, this is a bit dependent on how well you're trained with reading English. But for most people that have English as a first language, they can easily read this sentence, and they can properly produce the right spelling. So there's redundancy in the language in that it doesn't actually matter if you scramble a few letters. You can still undo these errors. But then if you overdo it, you can see that something went wrong, but there's no way you can, I mean, it's just too far away from any meaningful sentence for you to say what it could have meant before. And that leads me to this first distinction on the technical side. It's a different thing to detect that something went wrong and to just correct these errors automatically or from the information you're given. So here it starts out fine, and then you notice, okay, someone fell asleep on the keyboard. or something. Whereas if there's just a few little things, you may even not notice them while reading. Now, okay, I tried to keep the examples concrete in writing. The same happens with voice, right? Okay, I'm not so good at, I'm not out of my depth here, but I think there's certain variations in frequency and so on that we're completely oblivious to. If I have a more high or low pitched voice, you can still make out the patterns of language and sound and pronunciation. So there's certain things that are irrelevant, but then there's this lovely game, depending where you come from. But the game is you whisper someone in the ear, in their ears, some sentence, and they have to pass this on by a chain of whispering into people's ears. And what comes out at the end often has nothing to do with what you started with. So people are very eager to correct what they hear into something that's close enough in meaning to what they think might have been the original thing. And we're sometimes too eager doing that. Okay, so detecting errors, correcting errors, both things that intuitively we do all the time. And of course, also the options are, if you can correct the errors, then hopefully you corrected it correctly. Whereas if you just make out, I couldn't get it, you just ask to repeat it. The same is what computers can do as a countermeasure. You can try to build in redundancy so that you can still make out what the original meaning was. Or you can ask the other side, please send me that package again. Internet protocols have that all built in. But that's a bit boring from the coding side. So we'll mostly focus on those, on correcting codes, but detecting is a prerequisite. Yeah, to the computer world, so where does noise come from for us? Computers typically communicate with electrical signals, but that's not the only thing. So if you have copper cables, there could be inference from magnetic fields, electromagnetic fields that just interfere with the signal that you get. We usually abstract away from the physical details. We'll just transmit a string of bits. And you can think of different ways of what could go wrong. What we'll basically assume is that the clock is not perturbed, but the signal might be. So it could happen that one of the bits was a 1 and flipped to a 0 or vice versa. But we assume that the timing is correct. It's much more tricky if you also allow that there could be bits inserted or deleted from your bit string. If you think about transmitting something across a wire, that's actually a reasonable assumption. You usually have a separate clock signal, and that is somewhat stable, whereas interference might be twisting a bit to the other side. And the goal is to have a way to send data across such an unreliable communication channel to still allow reliable communication. As for humans, we have the two options. If we just detect an error, we can request a retransmit. Sometimes that's the best option, but for some communication channels, there's no option of resubmitting. Then you want to build in enough redundancy to correct it straight away. I think it's quite clear that you need some form of redundancy to correct errors or even detect errors, simply because if you have no redundancy built in, any kind of change that the channel does to your message, the receiver will just have to take as, oh, you meant this other message, and there's no way for them to know. So you have to send more bits than the plain text, the plain message that you're trying to transmit. In a way, that's the opposite of compression. We're making things longer now, whereas we tried to make them shorter before. But you should think of them as going hand in hand. Again, it's a pipeline. If you send something across a communication channel, you first want to compress so that the message becomes short, and then you blow it up, but you blow it up in a specific judicious way with building redundancy, and that's helpful, not random things. Okay. I want to close this part with getting your thoughts on two questions. Just now, I know that some of you maybe have seen this. If you've done some more electrical engineering undergrad, maybe this is, I'm telling you baby stuff here. If not, then you may never have seen this, and it's totally fine. So it's just your gut feeling. What do you think should be or could be possible here? And the first question is, if I want to send 100 bits as a message, and I want to detect whether there's one bit that flipped, how many bits of redundancy would I need to do that? What do you think? I think yeah, we can discuss the results briefly, but I'll only really show you the answer tomorrow. Keep up the tension a bit. Yeah, maybe we should have specified. Just send one number, or you can send no idea if you really feel like you want to send no idea. But several people send so and so many bits and so on. Send just the numbers so that we get a nicer word cloud. All right, I mean, you can finish sending your things, but because quite a bunch of people are done, here's just what people send. I won't comment on whether any of these are correct, right? We'll see tomorrow. Of course, a bit disappointed that nobody said 42. So I have a second question, which is the very same thing, but with correct instead of detect. So probably we need more bits for that. But other than that, maybe it's not obvious. So here's the second question. Again, just send the number, no units. Unless the unit is clowns, I guess that's fair. I don't know. Well, as before, I said I won't comment on any of it. I'll keep them on Slido and we'll discuss tomorrow.